Last time on Dragon Ball Z.
After 10,000 years, I'm free. It's time to conquer Earth.
Oh, I guess what's going on? Memes here. Yes. We're totally taking some stuff out of here. It's all right. It was appropriate. At least I felt. But all I know is I was going to do a completely different video, and whilst looking up Fermi's paradox and then getting ready to ask the questions, are we a prime example of Fermi's paradox? Basically, once any sufficiently advanced society hits basically the social media era and the velocity of information, so we just self-annihilate. And then Google recommended something totally different. So here we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey. All I know is... Ooh, that's really loud. But all I know is... Hey, the algorithms have done me pretty well so far. At least they tend to show me what I'm looking to seek here. So, what the heck is Fermi's golden rule? Alright, thank you, Power Rangers. Alright, we're good with that. Alright, so Fermi's golden rule is basically describing, let's say, maybe the perturbation, with whatever little stuff that it takes to achieve a different Eigen state. Go Eigen Rangers. Now, we go to our friends here of the internet. We start off with Wikipedia. Again, take it for what it's worth. But as we can see, Fermi's golden rule. In quantum physics, Fermi's golden rule is a formula that describes the transition rate, the probability of a transition per unit time from one energy eigenstate to a quantum system to a group of energy eigenstates in a continuum as a result of a weak perturbation. The transition rate is effectively independent of time, so long as the strength of the perturbation is independent of time. Oh, that's some very interesting stuff right there. And is proportional to the strength of the coupling between the initial and final states of the system, described by the square of the matrix element of the perturbation. Apparently, squares are very important. Basically, very often in physics, it's been said, well, if you see something, it's like, try squaring it. Try taking the square root. Occasionally, you can cube and stuff and things. It's kind of like you take the square root of the fine structure constant, you get as, I believe Professor Feynman referred to it as the true fine structure constant. Some people refer to it as Joe 1. But, yes. As well as the density of the states. Oh, energy density strikes again, it seems. It is also applicable when the final state is discrete, i.e. not part of the continuum. I believe Professor Unruh may have mentioned something about that before. The potential firewalls, and maybe it wasn't about the continuum, but maybe unitarity was not necessarily... he didn't know what was going on. May or may not be complete. And that's why I talked for an hour about it. If there is some decoherence in the process, like relaxation or collision of the atoms, or like noise in the perturbation, in which the density is replaced by the reciprocal, the decoherence bandwidth. Okay. It's wonderful. Go over to hyperphysics. This is a beautiful site. Apparently, they put all this stuff up, and then they would provide DVDs and stuff to people that were interested. I think you had to buy it, but all I know is there's a lot of good stuff on the internet, in my opinion. Transition probabilities in Fermi's golden rule. One of the prominent failures of the Bohr model for atomic spectra was that it couldn't predict one spectral line would be brighter than another. From the quantum theory came an explanation in terms of wave functions. And for situations where the transition probability is constant in time, it's usually expressed in a relationship called Fermi's golden rule. In general conceptual terms, the transition rate depends upon the strength of the coupling between the initial phase of a system and upon the number of ways the transition can happen, i.e., the density of the final states. In many physical situations, the transition property is of the form of the lambda sub I of f equals 2 pi divided by Planck's constant. And then you multiply that by the matrix element for the interaction, and you square it, and then you multiply that by the density of the final states. Fermi's golden rule. It's very beautiful. Oh, correction from yesterday's video. I totally wanted some speculation to be is the composition of whatever it initially was. I'm just going to guess was the reduced Planck's constant, because when you put the thing in from yesterday, then it equals 1. Because Planck's constant basically just has the reduced Planck's constant just multiplied by 2 pi. So I totally was hoping to be some other things. I hadn't actually put that in yet because I was lazy, and then I put it in today. So just correction there. I apologize. The transition probability lambda is also called the decay probability, or decay constant. It is related to the mean lifetime tau. Oh, that's 2 pi of the state by lambda equals 1 over tau. Oh, it's 1 over 2 pi. Cool. The general form of Fermi's golden rule can apply to atomic transitions, nuclear decay, scattering, a large variety of physical transitions. Some may say it's a transition between different Eigen states. So it's, I don't know. I was going to use
I lose that meme. I don't know what that meme is about.
Medics are important. I'm just saying that becoming more familiar a little bit. Do I still really know what's going on? No. But I'm attempting. Might be doing it badly, but we're slowly doing it badly. A transition will proceed more rapidly if the coupling between initial and final states is stronger. This coupling term is traditionally called the matrix element for the transition. This term comes from an alternative formulation of quantum mechanics in terms of matrices rather than differential equations of the Schrödinger approach. The matrix element can be placed in the form of an integral where the interaction which causes the transition is expressed in a potential v, which operates in the initial state wave function. The transition probability is proportional to the square of the integral of this interaction over all of the space appropriate to the problem. We can see the wave function of the final state there, wave function for the initial state, and this is the operator for the physical interaction, which couples the initial and final states of the system. Now, at least for electromagnetism, at least Professor Wolfram was going into a little earlier, what's the fine structure constant is for? Basically, it's a dimensionless term that's a measurement of the electromagnetic coupling. I also should probably clip out some of the stuff he said about it's going through a little bit of dimensional analysis. I may or may not have reminded him of a couple of terms. This is the kind of integral approach using the wave function is of the same general form as they used to find the expectation value or expected average value of any physical variable in quantum mechanics. But in the case of expectation value for a property like the system energy, the integral has a wave function representing the eigenstate of the system in both places of the integral. Oh, that's pretty nifty. The transition probability is also proportional to the density of the final states, for it is reasonably common for the final state to be composed of several states with the same energy. That sounds like energy is conserved. Hey, power to the laws of thermodynamics. They help us do stuff and things. Such states are said to be degenerate states. This degeneracy is sometimes expressed as a statistical weight, which will appear as a factor in the transition probability. In many cases, there will be a continuum of final states. So the density of final states is expressed as a function of energy. All right, that's nifty. And again, one of the reasons that we do this is, do I have the answers? No. I'm looking to try to help folks out. And occasionally, you never know who's watching. Because that's the beautiful part about the internet. You may have it targeted for somebody, and that's great because you can put all the cute cat videos, the random jokes videos and tricks and pranks, yada yada yada, and oh, here's some rage bait here, get that dopamine going. That's cool. I mean, you could totally do that. I ain't the boss of no one. I'm just saying that if there's a little bit of information that may help somebody, I don't know, think of something a lot more useful than maybe rage bait. Again, just the opinion of a dude on the internet. Maybe we can actually help level up society. Now, again, sometimes a little bit of charitability can go a long way.
We won't be going hungry if we do this, that's for sure.
Dude, my hat has made over $10 tonight.
I guess I'm going to have to wear a cowboy hat on here with you next time, too.
Howdy.
I'm just saying, good hats can make a big difference. But especially if you're going to measure energy potentials and stuff. I could probably do some more stuff on this, but there's a lot of other stuff I need to do. Now I need to go run. But please said, everybody, thank you all for watching. And no matter what happens, again, we have yet to...
World exists on the top of a giant turtle.
Thank you, Professor. Peace out, everyone.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.